Okay, welcome back. So we can see, again, in the stata output, you can see that it shows us our statistic. And again, the value of the sum of the observed minus expected squared over expected, the sum is 7.044. And that corresponds, when comparing that to the chi-square distribution with 8 degrees of freedom, a p-value of 0.53. Big p-value, no evidence of lack of fit of the model. So you would say that based on this, you think there's reasonable calibration. By the way, this statistic, well, let me come back to that. First, I want to talk about the Pearson chi-square. The Pearson chi-square statistic is the one we talked about where every individual essentially is given their own column. Actually, it should be every covariate pattern is given their own column, but in this program, in SysStat, it's every individual is given their own column. When we look at it in Stata, in fact, every covariate pattern will have its own column. So you'll see there's a discrepancy between the SysStat version of the computation of the Pearson chi-square and what we have in Stata. But notice the tip-off to the fact that you have a problem is that the degrees of freedom for the statistic is 185. 189 observations, 185 degrees of freedom, because they followed the rule that it was a number of observations minus a number of parameters estimated, and there were four parameters estimated: beta naught, beta 1, beta 2, and beta 3. So this is 185. So you know that this p-value is nothing to take seriously. Okay. Now, what I had wanted to mention before is that it's very important when you do a study where you develop your own model. It's very important that you do a goodness of fit test, especially if you're doing a predictive model, because there the interest is to estimate the probabilities correctly. And it's very important to do this so you can get some sense of whether the model is producing accurate probabilities. But what's also very important is that if you're developing a model that you hope other people will use, and why would you develop a model if you didn't want other people to use it, then the model needs to be validated. Okay, so you need to have some additional individuals that you use this model on to see whether or not the probabilities that are generated by this model also apply to a data set that wasn't part of creating the model. Okay, that's called a validation data set. And when you apply this model to a new set of subjects, then the degrees of freedom for that test will not be 8, but it will be 10. Okay, so there's 8 degrees of freedom when you assess the performance of the model in the same data set that you developed the model on. But you don't have to lose 2 degrees of freedom when you take some new group of patients and you use the same model that you created based on another group of patients, and you don't lose those additional 2 degrees of freedom. Okay? In any case, you can see that you have... Now, I'm not going to talk about the deviance chi-square statistic. It's very similar to Pearson. It has the same problems. You can see it has the same degrees of freedom. It's a slightly different way of calculating it, so we don't have to go over it today. But the conclusion that we can see here, if all I had available was SysStat, you can see here that, again, the observed and expected counts over the 20 cells are pretty close, and the overall test statistic is pretty small, p-value big, suggesting that the model fits. This is SysStat, where it fixes the cut points at 10%, 20%, 30%, and so on. And what you can see is that there are no women in this study who had probability above 60%. So as a result, all of the women are put into deciles 0 to 10%, 10 to 20%, up to 50 to 60%, and then there is nobody else. And so therefore the degrees of freedom here is only 4. Because again, it's G minus 2 degrees of freedom. There's only 6 deciles. They're not really deciles, but there's 6 groups. And so you only have 4 degrees of freedom. And the problem is that when you have that few degrees of freedom, the test statistic always indicates that the model works, so that it has no statistical power. So the problem is that in that case you have no statistical power. And in other cases, especially with large sample sizes, you have too much statistical power, where the test statistic will essentially tell you that the model doesn't fit when really it was pretty good. It's just that you have too much power. So that's the balancing act that you do. But you want at least 10 groups, because this is not effective. Okay, so here's how you do it in Stata. In Stata, here, you've seen this particular output before. We run the model, again, we're doing logistic regression. Low birth weight is a dependent variable, and last weight and race, and I've indicated that I wanted it to create the dummy variables for race for me, which it did. And so here you have your model, and again, step by step, it's iterated into a solution. If I said to you, again, when you look at this model, is this a better model than the naive model? Of course it is. The p-value is less than 0.01. The value of the likelihood ratio chi-square statistic is 11.4, so it's big. And so we would conclude that this is a better model than the naive model. In fact, if you look at the wall test statistics, it would indicate that there's nothing else I can really get rid of. At least in this course, if you have one significant dummy variable, then you keep them all. Now, obviously, as you go more into model building strategies, that wouldn't be the way you would necessarily go forward. There are other things you could do, but for the purposes of what we're doing together, this is really going to be our model. So after you run the model, you simply say LFIT group 10 table. Okay, so LFIT alone basically gives you this. If you don't say anything about group 10 table, LFIT will give you the the Pearson chi-square statistic. It tells you here that the number of covariate patterns is 109. So it wasn't like Systat thought there were 189 covariate patterns and it made a separate column for each person. But in fact, there are only 109 distinct covariate patterns in these data. And so when it does the Pearson chi-square statistic, it knows that there's only 105 degrees of freedom. Only is not, it's not that it's, a small number. It's a huge number. And so again, indicating that the Pearson chi-square statistic would not be a valid way of assessing model performance. But if you say group 10 table, then it will create 10 groups. If I said group 100 table, it will create 100 groups. That wouldn't be a very good idea if you have 189 women. But if I had 10,000 women in my study, I might very well want 100 groups or 200 groups. Okay, but here, group 10 table, and it creates the table for us. It tells us the cut points. Okay, so the first group had probabilities between 0 and 16.8%. The next group had probabilities between 16.8% and 22.2%, and so on and so forth. The last decile were women who has probabilities between 47.7% and 59.75%. Remember, nobody had a probability in this data set above 60%. And here you can see the observed count and the expected count in each decile. Again, looking at it decile by decile, looking at observed and expected counts, they match up pretty well. There are some discrepancies, but nothing very big. And again, that's indicated here when they do this test statistic with 8 degrees of freedom. The statistic is 7.61, and the p-value is 47.28%. So 0.47 is a big p-value, again suggesting that this model fits the data. Here you have the goodness of fit. We're going to do the goodness of fit test for the ICU data. And so we have here the vital status is the dependent variable, and we have age, cancer. We have a variable that we've dealt with blood pressure, where we've simply taken people in the 4th quartile of blood pressure versus everybody else. So being in the top quartile of blood pressure is what this is, a binary variable, just being in the top quartile of blood pressure, type of admission, and level of consciousness. Those are the variables in this model. And it goes through, again, same kind of questions I always ask. Is this model a better model than the naive model? And of course it is. The p-value is very small. So if you're interested in estimating the probability of dying in the hospital, you're much better off to know all of these variables than to know none of them. Okay, this tests the hypothesis that beta 1 equals beta 2 equals beta 3 equals beta 4 equals beta 5 all simultaneously equals 0, and you reject that hypothesis. Okay? Nothing stands out here as being a variable that we can get rid of. They all seem to be important variables. So now we're ready to look at the goodness of fit of this model. So we say again, LFIT, comma, group 10 table. And that will then fit the logistic model. And notice that we have, again, because I've said I wanted 10 groups, so we have 10 groups. And we know that the first group are individuals whose probability of having probability of dying in the hospital is between 0 and 1.05%. And we didn't have anybody die with probabilities like that, and we expected only 1/10 of one death. Okay, and similarly, we had of the 20 people in that first group, all 20 of them lived, and we expected basically 20 of them to live. And looking at the observed and expected counts, they're pretty extraordinary in terms of the way they match up. And when you do the test statistic, you can see that with 10 groups, 8 degrees of freedom, the statistic is 4. Compared to a chi-square distribution with 8 degrees of freedom, the p-value is 0.86. This is higher than it usually gets, but it's pretty good. It tells us that this model is doing a good job in estimating the true probability of mortality for these ICU patients. Also tells us that out of the 200 subjects in the study, we had 129 covariate patterns. And again, if you were to do this with Pearson chi-square, I'm sorry, it had 135 covariate patterns, which translates into 129 degrees of freedom for the Pearson chi-square test. Still, you can see way too many covariate patterns to believe this particular p-value, which is 99.98%. That's not accurate, because it can't be, because you have so many covariate patterns. So this is a good point for a break, and so we'll see you after that.